Determine whether the mean value theorem can be applied to each function, and if so, find the value of c such that f prime of c is equal to the slope of the secant line between a and b, or f of b minus f of a divided by b minus a. So just to recall a couple of things I talked about in my previous video where I explained the mean value theorem. This is a, and this is b, and this is f of a. And let's say this is f of b. Then here's your secant line, and that secant line has a slope. And let's say our function, I don't know, does something like this. That's your function f of x. Then somewhere inside this interval, a to b, it can't be one of the endpoints, but somewhere between the a and the b, there's another x value. We'll call it c. And at that x value, the slope of the tangent line is equal to the slope of the secant line. And in this case, looks like it's right about here. Okay, to apply the mean value theorem, recall, we have a couple of criteria. Actually, one less than Rolle's theorem. Rolle's theorem says f of a has to equal f of b, but if we drop that, we'll keep the other two. We need f of x continuous from a to b, so the closed interval, and we need f of x to be differentiable, or the derivative exists between a and b, so the open interval a to b. We don't care if the derivative exists at the endpoints. Okay, so if those two criteria are met, then we could apply the mean value theorem. So let's say, number one, let's let f of x equal the cosine of 2x minus the tangent of x on the interval, let's say 0 to pi. Determine whether the mean value theorem applies, and if so, find the value of c, where f prime of c is equal to the slope of the secant line. Well, can we apply the mean value theorem? In this case, we cannot, because of the tangent, the tangent being part of f of x. So f of x has a vertical asymptote at pi over 2 because the tangent function has a vertical asymptote at pi over 2. So f of x is not continuous when x is equal to pi over 2. So in this case, the mean value theorem does not apply. Mean value theorem doesn't apply. Well, let's look at a case where it does apply. Let's say number 2. Let's say g of x is equal to, let's say, the square root of 2 minus x on the interval -7 to +2. Now, is the function continuous? Well, the square root function is continuous everywhere in its domain, and the g of x is defined everywhere between -7 and 2. If you plug in any number from -7 to +2, you will be able to take the square root of 2 minus x, meaning you won't get a negative number under the radical. So the function is continuous. And let's look at the derivative, g prime of x. Well, the square root is the same as the 1/2 power, so we'll apply well, let's just rewrite g of x before we take the derivative. Let's say g of x is equal to 2 minus x to the 1/2 power. So the derivative, g prime of x, we'll apply the chain rule here and the power rule. So the 1/2 comes out front, decreases by 1 to negative 1/2, times the derivative of the inside, which is negative 1. So our derivative is negative 1 divided by 2 times the square root of 2 minus x. Now, is the function differentiable, or is the derivative defined between negative 7 and 2? And the answer is yes. It's not defined at 2. So the derivative is undefined. When you plug in 2 for x, you get a 0 on the bottom, but that's okay because the derivative doesn't have to be defined at the endpoints, only between the endpoints. On the open interval, negative 7 to positive 2. So we have continuous on negative 7 to positive 2, check. We have differentiable on the interval, open interval, negative 7 to positive 2, check. So the mean value theorem can be applied. All right, so now to apply the mean value theorem. So, just like with Rolle's theorem, this is a two-step process. Step 1, determine whether or not you can apply the mean value theorem, and then set the derivative equal to the slope of the secant line. Okay, so the slope of the secant line will be f of a, well, I'll use g because we're using g here, g of b, oh, we'll plug in the a and the b, g of 2 minus g of negative 7 divided by 2 minus a negative 7. And if we plug in 2 into the g function, we get 0. If we plug in negative 7, that's 2 minus a minus 7, or 2 plus 7, which is 3. So we get 0 minus 3. And on the bottom, 2 minus minus 7, or 2 plus 7, is 9. So the slope of our secant line is negative 1/3. So what we want to do is set the derivative equal to the slope of the secant line. And we'll solve for x. Okay, so our derivative is negative 1 over, so the derivative is right here, negative 1 over 2 times 2 minus x to the 1/2 power, and we'll set that equal to negative 1 over 3. So if the numerators are both negative 1, the denominators both have to be equal to 3. So that tells us 2 times the square root of 2 minus x has to be equal to positive 3. All right, we can divide both sides by 2. 2 minus x square root is equal to 3 divided by 2. All right, good. Square both sides of the equation. So we'll have 2 minus x is equal to 9 over 4. And then we could subtract 2 from both sides. So that'll give us a negative x is equal to 1 over 4, or x is equal to negative 1/4. So the slope of the secant line, or the slope of the secant line and the slope of the tangent line are both equal to negative 1/3 when x is equal to -1/4. So we'll say slope of the secant line equals slope of the tangent line when x is equal to -1/4, and that's our value of c. So c equals -1/4. And that about does it. So we have one example where we cannot apply the mean value theorem, one example where we can. So just remember, it's a two-step process. You can't just apply these theorems, the Rolle's theorem or the mean value theorem. Step one, determine whether or not you can apply it. And once the answer is yes, then you take the derivative, set the derivative equal to the slope of the secant line, and solve. All right, that does it for this problem. I hope it was helpful.